We start again. Good morning. No, okay. Just for the sake of the video, there will be a first part about formulas of distributed Bragg mirrors, just theoretical, some schematics. Then we'll do a COMSOL session where you simulate the different photonic crystal geometries. And then after, I'm going to show you like applications, like work that has been done with photonic crystal resonators. So you'll see something different than ring resonators, and how you would engineer the dispersion of a photonic crystal mirror. But you don't know any of these words for now, so let's just start. First of all, what is a photonic crystal? So a photonic crystal is a periodic structure with dimensions that are on the scale of the wavelength of the light. So that then when the light interacts with these structures, there will be interesting phenomena happening. Usually the properties, like the periodic structure, is usually referring to an alternating refractive index along the photonic crystal. So as you see here, along the x direction, you have these alternating layers. That just means that the dark blue layer has a high refractive index, which I labeled N high. And the light blue is a low refractive index. The two stuffs that you see on the right-hand side of the slide are basically what we call a unit cell. A unit cell is a cell where basically the electric field inside of it is symmetric or about the center. So you wouldn't be able to define a unit cell that doesn't look like that. So for example, if we were to take two of these layers and just stick them next to each other, they have the same material that these two unit cells have, but that wouldn't be a unit cell because the maximum of the electric field can only be centered within one layer. So that's why we define a unit cell where either the high or the low refractive index are in the middle, and then you have half of the other layer on the two sides. We talk about band gap when we have photonic crystals, and I'm going to show you why. Now maybe it sounds a bit, it doesn't make any sense, but later in the next slide, I have an example of what the band gap is. What I would like to focus, as I said before, about how the electric field and the intensity of the light looks inside these stacks of different refractive index materials, is these two modes that can propagate in this kind of structure. You have the dielectric mode, where if you can see, the electric field is going to oscillate like this. And then if you just do the square root of that, you find the intensity that has peaks in the high refractive index material. This is usually called the dielectric mode, and that's because usually the dielectric has a high refractive index. So that would be your silicon nitride, or in this talk later we'll see gallium phosphide or 3,5 materials. So the other case where the electric field maxima are centered in the middle of the low refractive index material, they're called air mode, because basically it can be done that the two layers are one, a semiconductor, for example, or silicon nitride, and the low refractive index is air. Basically, that the material is missing. Air has a refractive index of 1. If you were using silicon oxide, it would be 1.44, but it's called air in literature, or like, you know, people call it like this. So these two modes look very similar, but clearly they have different energy profiles, given the fact that they're centered in a material with a different refractive index. And that's what we call a bandgap. So let's look at this way. If you don't have a photonic crystal, so like this, it's just a bulk material, gallium arsenide, or if you have a waveguide, what you will have is that in frequency, this is a band structure, like exactly like the ones that you have for electrons in a periodic lattice. And it's the same concept of like this periodic lattice that now is refractive index for photons. For electrons is potential. What you have is for a waveguide or a bulk material is that there is no bandgap. Like you have the wave vector as you go higher in frequency, all the modes, they are just like connected to each other. As soon as you start putting like a contrast in the refractive index where there is a small difference between the high and low refractive index, then a photonic bandgap starts opening up. All right. If you make this difference very large, like for example, here it has gallium arsenide and there, the bandgap will become even larger. So the size of the bandgap depends on the index contrast, which is the difference of the two divided by the sum. That's not important. The concept is that the bigger the difference, the larger the contrast, and so the photonic bandgap. So what you see is that at this point, the dielectric and the air mode, they're like touching each other, right? So in a waveguide, you don't see any difference, like it's the same mode, you know? This point is one point. Here it starts being different. And so, yeah, nothing. Like if this is happening because of what I showed you before, that the peaks of the intensity, they are centered in the other materials. So the energy overall is different. And so you have the dielectric mode is going to be this one down here, and the air mode is going to be the higher one. You are going to simulate photonic bandgaps later, so you will see how this happens, and you'll try to optimize the dimensions of like the structure such that you have an optimized bandgap. But so to enhance this index contrast. Yeah.
How do you know the air mode is above and the electric mode is under?
Yeah, I mean, that you have basically simulated, let's say, but so how to say, basically, if the electric field is in the high index material, it's like to achieve basically the same proportionality between the energy and the frequency, you need a lower frequency. If this is like empirically, let's say, if instead it's centered in the air mode, basically the product, let's say, between the intensity and the electric and the refractive index is smaller. So you need a higher frequency to get basically to the same energy, let's say, you know, because it was supposed to be the same mode that it got split. And now the energy is in like a different material mainly. And so you can see it like this. All right.
What is the refractive index of the photon bandgap? Is it different from the refractive indexes?
But sorry?
What is the refractive index of the photon bandgap?
Oh, that is a good question, because one can look into this and it's not easy to find an answer, because in theory, like effectively in the bandgap, there is no photon that can propagate, right? Because like your photons can only propagate in wherever you see a blue line, right? That's where you have a mode. But in here, there is no mode allowed. So that means that if a photon comes at this frequency, it will be reflected because it can't propagate. Yeah, this was important. Thank you for the question. But is it clear? Like, it's like those electrons that if there is a band gap, then it's like, here they can't be here. And here is the same for the photons. So to find a refractive index in there is not easy at all. Like you would have to find a model of like the propagation, or let's say the penetration of the photon inside the band gap before it gets reflected, such that it doesn't involve the refractive index, because actually you can't calculate it. Because the refractive index is basically like the bending of these bands, right? In a waveguide, it's just basically given by the tilt here, the inverse, but okay, you know, so that's how the refractive index, what it is in a waveguide. But here, you can only calculate the refractive index wherever you have these bands with the tilt, the slope. All right. These might be useful for your future if anyone decides to go after this. Actually, when you will do like the things later in COMSOL, you will see that if you want like a one-dimensional photonic crystal, like I showed you, but planar, so in a waveguide, and I'll show you what types of configuration we can do, you will see that these formulas, they're not enough to actually know exactly how you design your band gap. A full 3D simulation will be needed. And that's what we will do. But in general, like if you want to have like a way to first like estimate how big these layers should be, how thick they should be to reflect a certain wavelength, this is the formulas that you need. So to reflect a wavelength lambda b, the alternating layers need to have a thickness of lambda quarters. But what does this mean? It means that this formula here is valid for both of them. So it's not the sum that is lambda quarter. So it's each product of the thickness times its refractive index of that layer is going to be equal to lambda quarter. So you can calculate both thicknesses, like here. Yeah. And that will give you like how thick the two layers should be with respect to each other. Then the sum of both will give you the width of the whole unit cell. But we'll look at this unit cell business better for COMSOL. As another formula, we have that the bandwidth of the reflector relative to its center frequency, so it's a relative band gap, it's like doing the bandwidth, so how wide this band gap is, divided by the center frequency of the band gap, is going to depend on the index contrast. So again, the bigger the index contrast, the bigger the bandwidth, you know. And the question now is, we said that the photonic band gap can reflect frequencies that would want to propagate within this band gap. And now the question is, how reflective can these distributed Bragg ratings be? And the first formula is just for the sake of completeness, where basically it's really accounting for everything. You have like, okay, we have this stack of materials, and we will have a specific material that brings us to the mirror. And after the mirror ends, there will be another material, right? So the first, okay, this is like, if you want to consider everything, this is the formula you need, where M is the number of pairs of alternating layers. So, yeah. But now let's suppose that the material that you use to come into the mirror is exactly the same as the first unit cell, which is usually like what happens if you have like a waveguide. You come with the same material that is the dielectric, then if you start with the high refractive index layer, that's the case. And then you have a mirror. At the end, let's suppose you cut it because it's finished, like your waveguide is before, right? That last layer is going to have a refractive index that is equal to the low index material, so the cladding or air. So then you can get into this much nicer formula. What I want to show you here is that this ratio in these brackets is smaller than 1. So this means that the more unit cells you put, like the more pairs of alternating layers you put, this ratio is going to go down to 0, right? Towards 0 at the top and the bottom of this fraction. So that means that if you have many unit cells, your reflectivity will tend to 1. So that means it's perfect reflection. Then, of course, this can go as long as you want, like you can put 200 unit cells. Maybe that's actually very close to 1. But if realistically you put like 10 or so, it depends on the material, on the refractive index contrast. But let's say that a good mirror usually has a reflectivity of like 99.995%. So it has to be very reflective. And yeah, okay, here I don't have the formula, but basically in a Fabry-Perot resonator, so where you have 2 distributed Bragg mirrors on the sides reflecting light, this reflectivity is what you're going to use to calculate the quality factors of your resonator. Like, depending on how good they are, of course, they will have lower losses, like that they reflect all the light and they don't let light leak through. So that will give you much better resonators. So what you want to design is mirrors that are very highly reflective. And now, how does a photonic crystal reflector look like? This is what you will be doing in a few minutes. And what you can design on a chip. These are like top views. So we are looking from the top. It's a 1D photonic crystal because if you consider your incident light coming from the left, then it goes in and it's just a series of holes. A 2D photonic crystals would have been like a grid, like if you were putting all these holes also down and up. So this is not what we are doing here today. So there are several implementations that one can work on, and it's basically a waveguide patterned with holes. So what you see here is basically the high refractive index material, the low refractive index material, the high refractive index material, because whenever you take out material, then the refractive index will be lower. In the other case, it's going to be a smaller waveguide with this external crenulation. It can be rectangles, it can be sinusoidal, so it can be any shape, it can be a triangle. You know, the thing is that if you have this modulation of the width of the waveguide, then you're also there creating a difference in refractive index. And the same has to be said for the pillars. So this is basically like the top right solution, just without the waveguide in the middle. So we will talk about it later after the exercise session. But yeah, so this might be relevant, but I like to think about it this way. Like, if these are mirrors, right? Like, how do they behave with respect to the light that is coming in? Like, if you have a mirror in your room, that usually you say that the electric field at the mirror is 0 because like there is this reflection. The electric field coming back has exactly 180-degree phase shift compared to the incident one. So the electric field at the surface is going to be 0. So what about here? Like, how do these mirrors behave? Are they perfect electric conductors? Are they perfect magnetic conductors? And what you need to think about is where the maximum of the electric field is. in this case, supposing there is a waveguide here, what you see is that the electric field is going to be 0 for the dielectric mode in the middle of the hole, right? The maxima are going to be in the dielectric, right? So what it means is that you have maximum electric field at the beginning of the mirror. That means that the magnetic field is going to be 0. And so this is a perfect magnetic conductor. In this case, it's the other way around, because if we come like this, let's say with a waveguide, this is the first unit cell, it means that there is a path here where you'll have the first void of like low refractive index material. So you will have the maximum dielectric field in here in the pillar for the dielectric mode. That means that the electric field here is going to be 0. So this is a perfect electric conductor because the electric field at the beginning of the mirror is 0. And this is the same for this other solution, which basically is exactly like this one, right? It's just the case where the waveguide didn't go to 0 yet. So you see the electric field maximum will be in these rectangles, and it will be 0 at the beginning of the mirror, and that's also a perfect magnetic conductor. So does it tell us much? No, but it's still nice to remember. Like, yeah, I think it puts everything into like together to get used to it, or like to remember some interesting things. So you will simulate all these things. Now, how does a band gap look? Like if you were taking COMSOL, I don't think we have time to do this simulation. I will give you like the information that you need if you wanted to run this simulation, but it takes some time to be able to plot all those points. Okay, that's an interpolation clearly, but if you wanted to simulate the band gap for each like wave number, these are all pairs of points basically, right? For TE and TM modes. So I will tell you how it's done, but yeah, I think this you already know. Like if you were to simulate a unit cell and you want to, let's say, reduce the simulation time, first of all, because nobody wants to stay there forever, and also like isolate like TE or TM modes, then you can put some symmetry planes. Do you know this for the waveguides? That you have like a perfect electric conductor or magnetic on the vertical or horizontal planes so that the other mode family disappears. Okay, this can be done here as well. So that's how I have that plot where basically I can say for sure that the blue ones are TE modes and the orange ones are TM modes, because I put the symmetry planes so that I'm sure that I'm only looking at a certain mode family. So not all those modes that you see in that picture are guided. Whenever we are in that gray area, which we call light cone, that means that the modes are not guided, like they are like in the cladding or something like that, you know, they are not in the higher refractive index material. So one can calculate the light line, that is basically the edge of this light cone, with this formula. It's just a dispersion relation. What you need is K is the wave number, and is going to be the refractive index of like that material. So yeah, like the bulk. Yeah, so it's just interesting to know, you know, this is basically the edge of the first brilliant zone. This wave number will go from 0 to 50, let's say from minus 0.5 to plus 0.5. It should be symmetric about the origin, and then it's going to repeat like in an electron case, right? So you can go all the way down to 0, but what happens is that this line is going to come down. You might only have this mode close to 0, and it's not even relevant. Like what you're interested in is the edge of the first Brillouin zone. That will give you the modes that are actually confined in the dielectric and like what you would expect. That's how you calculate it. The other ones are like a bit in the oxide, they are a bit outside. It looks a bit weird. So we are mainly interested in these 2 points at the edge. What is true, of course, is that a band gap is a band gap if no light can propagate in it. So let's say there is a higher order mode up here that comes down like this. That is going to limit your band gap, because that means that in this frequency that you thought was a band gap, actually there will be another possible mode more inside the Brillouin zone, and you have some propagation in this other mode. So what you want is a clean band gap where you have like no modes, at least of the same mode family, within the band gap. Just about terminology, let me just say it out loud. Let's look at the T mode. It's a very nice band gap, like it looks big, especially compared to the TM mode. But what you can say is that, you know, in these 2 regions, the TM mode can propagate, right? So it's not a perfect band gap. In the T mode family, it's really a band gap. And so what we call, when one mode family can propagate and the other one cannot, we call this an incomplete band gap. What you will see here is that this narrow region, it's a complete band gap, because in here, there are really no modes allowed. Yes. Of course, like depending on the thickness of your waveguide, things like this, if the waveguide is very thin, what you know is that the TM modes cannot really propagate properly, or at least they will be very lossy. Is it right? Because it's thin, so it's better for the T. So depending on what resonator you are dealing with, this problem might not affect you. Like this is, for example, for my case, when I do mine, I don't care about the TM because my waveguide is very thin. So I know that if there are modes in the TM family, like they will already be so lossy, I don't care about them. So what I do, I try to maximize the T band gap. If instead you had a waveguide that is a bit more squared and you're interested in reflecting both of them, then you would take care of like still trying to maximize both modes. So probably the T band gap would be smaller, but the TM would be larger. And so what you would want to do is to match them such that they reflect exactly the same frequencies. This is not the case in the talk, but just for you to know, this is not a good photonic band gap for TM modes. It's very, very small. All right, now we are about to do COMSOL. Just as a thing, because I think that when you did the waveguide simulations, they gave you like a refractive index code for the silicon oxide. Is it true? Okay, so here I give you this for gallium phosphide, that is this 3,5 material we are going to use. You just copy these 2 things in the parameters and it should be there, right? But we are going to do it together also. As I said before, we are going to use symmetries, especially here to just look at the T mode family. And so you'll have the perfect electric conductor that looks like the one on the left. This, as you see, it's an example of a unit cell where you have a hole, right? If you can see. So it's just a waveguide pattern with a hole. We use the symmetry so that it would double this way, but also vertically, so we just simulate half the thickness. And then the most important thing, and I think this is what's new from this session especially, is this Floquet periodic condition that we will need to add Because if you were just simulating something like this is going to be terrible. Like it's just a piece of material with a hole. So you'll have a lot of scattering because the light goes in and it's like, what is this, right? But if you ensure that there is periodicity in this direction, that means that you're saying whatever is on this side is also what's on this side. So that means that you are making like an infinite amount of these exact unit cells one after the other. So of course, with this, you'll get a band gap and everything. You could be able to like estimate the reflectivity, but it's only going to be for like an infinite amount of unit cells. Realistically, you will pick how many of these unit cells you put. And so, yeah, maybe the band gap is big, but it won't reflect as 200 of them. So yes, I think we should go to COMSOL now. How do I do this? Wait, I will stop sharing and share the other. What? Hello? Do you know how I change what's going on here?
Close the lights.
Ah. Oh, okay, perfect. Thank you. Are we all here? Okay. But are we all there? All right. So I think, you know, we should go to Model Wizard, but can you see properly? It's a bit small, right? If I knew how to make it bigger.
Do that, or does it help?
All right. How do I do it?
It's not too bad. In the first, the whole first row is in.
I don't know. Like, if you know how I make it bigger, you can tell me because actually I don't. I tried. I'm just okay. Yeah, this is also my no. All right, let's try. Or I don't know if you want to come and see, but I don't have the keypad. Maybe. All right, Model Wizard. As I said, we need to do a 3D simulation. You also saw it. And maybe this is the first time you do a 3D simulation in COMSOL. All right. It's a nightmare, as in that the simulations will take much longer than the 2D waveguides that you have seen. So we'll try to find a trade-off of the mesh that we use such that, you know, for today, it won't be the most accurate, but we won't spend the day waiting for this. So we go 3D. Then this is the same. We go to optics, wave optics, and then we go to frequency domain. Are we all here? All right, so we put it. We go to study, and what we put is this eigenfrequency. That basically will calculate the resonant frequencies of the structure that we give it. That's what we want. So are we all here? All right. So let's define a few parameters that we will need.
How to go to study again after adding?
You just double click and it should start. Is it all right? Okay. Okay, now let's go to parameters. And we put, for example, the waveguide width, we say W, and we write 700 square brackets nanometers. And if we want, we can write waveguide width. Then we put the lattice parameter that is going to be just A for simplicity. And we put, I don't know, 500 nanometers. Let's just call it pitch. Then we define this lambda 0, LDA 0 as 1.55 micrometers, and we say that this is the operating wavelength. Then what we need is the frequency, like the operating frequency, and we go with the speed of light that is already in COMSOL is C underscore const divided by lambda 0 that we just defined, right? And this is the operating frequency. Then the material thickness, we call it thickness. Let's do 300 nanometers. Now, nanometers thickness. All right, then we need this parameter that is going to be like the wave vector. This is going to be the wave vector like at the edge of the first brilliant zone. So it's just going to be 1. And then we define another wave vector that could span over the whole brilliant zone. And we call it K underscore X, and it's going to be given by K underscore X underscore N, that is what we just defined, times pi over A. So if we leave it like this, with kappa x n equal to 1, we'll simulate the edge of the first brilliant zone. If you start changing K, X, N to smaller values, you'll get those plots that I showed you before with the Venn diagram, right?
What is XN?
Kx is the wave vector. Kxn is just for the simulations, like if it's equal to 1, you are simulating the edge of the first brilliant zone. If it's smaller than 1, you are like getting all the points within the first brilliant zone. So like, you know, the plot I showed you before with the Venn diagrams of T and Tm, like if you just put 1, it's going to be the final point. If you were to run a simulation where you sweep across like many values below 1, you would get that plot. Yeah. Are we all here? The last parameter that we need to simulate the holes is this radius. And let's put 150 nanometers. I think we have everything. Are you there? Because I'm going to change screen here. Like I will exit the parameters. Sorry. Are we okay? Okay. So we go to component. There is a definitions tab below. You right click on it and you select variables. What we are doing here, we are defining the refractive index for gallium phosphide. All right, so if you have my presentation, you can just copy and paste those two parameters that I said before, that are this LAM and NGAP. So please do that. Are we done? No. Otherwise, if you have to look for the presentation, you can also just write 3.05, which is also the refractive index at the frequency that we are going to use. If you wanted like a frequency dependent simulation and everything, which actually it is, because it depends on what frequency the eigenfrequencies are, but are we ready?
Yes.
All right. Like I just copied them from the presentation, or I mean, you get to definitions, you right click, and there is variables. So there, if you put these two, because the n gap depends on lam that we just defined as this lambda naught. It's a parameter from COMSOL. All right, let's go to geometry, which we like more than that. So let's right click on geometry and go on work plane. Now we made like a 2D work plane, like let's call it also. Let's go back to geometry, click on it and change the length unit to nanometers because that's what we used. Done. All right, so also let's add our geometry. So in plane geometry, we right click and we put a rectangle. This is going to be our waveguide, right? Before patterning it. Geometry, plane geometry. So we put a rectangle.
How do we get this holes? This one, yes.
Ah, no, I called it. It's just the work plane. It's the work plane that we did before. So if you clicked on geometry and you, oh, what?
Work plane.
Yeah, work plane here. I put work plane. Yes. I don't know why before the work plane was there, there weren't all these things, I think. Do we have it? All right, rectangle. So this is going to be our unit cell. So it's going to have a width that is equal to the pitch, so A, and the height is going to be equal. We said we want to simulate half of it. So it's going to be equal to the width half. We defined it as W, yeah. Ready? So we can do it like this. This is just a rectangle. Now we go on plane, what is it? Plane geometry again. And what we select is a circle. Now we are going to make the hole. So the circle is going to have a radius that is equal to r holes. We defined it like this. And then given that we want to have like only half, we are going to say that the sector angle is not 360, but 180. And also, given that we want the hole to be centered in the middle of this waveguide, what we can do for simplicity, we can say the position center, and we move it by half the pitch. That's it. Perfect. Do we all get this in like 15 seconds? Done? Yeah.
Why is it not minus a?
Because if you do minus a half, it's going to put it so center, so it means that we are taking this point as the reference for the hole, right? If we put minus, it's going to put it like here. Because this is the zero.
If we don't write anything,
It is going to be here.
the
Because
center
this at center of the hole is going to be at zero.
in the corner, top left, bottom left corner.
Yeah.
Right.
Yeah, it's plus a half. This is a. So half is just going to be this.
Okay.
Right? A is the pitch.
Yeah.
Are we ready?
Yeah.
So now what we do is we only have like a whole, like a semicircle and a rectangle. What we need to do is to define the difference between the two so that we can like carve out the hole from the rectangle, right? So we right click on plane geometry. We go to Booleans and partitions. Are we here?
Yeah.
All right, and we do difference. All right, there we say objects to add, we take the rectangle, then we select objects to subtract, and we take the semicircle. If we do that, we just get what we wanted. All right. Thanks. All right, I need to go forward. So we go back to the holes. So that's not the plane, what is it called? Plane geometry is just the holes. We right click and we select extrude. That means now we are going into 3D. We have our plane, our planar drawing. We need to make it, bring it up, like, you know. Okay, so here it says distance. So the work plane that we want is selected, right? And what we need to do is do half the thickness because we said we were only simulating half, right? So we write the thickness divided by 2. Beautiful. Ready? All right, so, but now what we miss is the cladding, right? So we go to geometry and we make a block. So the block, how does it need to be? So it has to have a width of A because we want it to be flush with the unit cell, right? It can't be larger. Otherwise, after we put the periodic conditions, we are going to have a hole between this unit cell and the cladding, right? So the width is going to be A, that is the pitch. Then this is basically how big do you want it, you know, like it's just the cladding. So now we are doing the how much we want in this direction, back here, and on top of it. So let's say that like 1.5 micrometers is enough. So let's do 1.5 E3 and the height the same. Okay. Then I'm wondering, yeah, perfect. So here it looks like we destroyed everything, but if you select this thing up here, I don't know if you see, you can see the transparency, right? I have the cursor there, up here, the top right, you can see the structure, otherwise it's just like this. It doesn't matter, right? If you imagine it, you are happy with that. But if you want to see it, then, and so let's call this block cladding so that when you see it, you know. It's just, you know, it's like when you simulate the waveguide, right? You have a box around it. And I don't know how you chose how big it has to be, but basically what you need it to be is like big enough such that your electric field doesn't get there. So maybe 1 micron is enough, or maybe we need 3. For my experience, 1.5 is good. Maybe it can be smaller, but you know, it's just to make sure that your electric field is not perturbed by these boundary conditions that we are going to put. All right, materials. So now we need to define the silicon oxide that if you want, you can use whatever model you have been given in the past few days. Otherwise, you just do right click, add material from library. And here, I think that if you go to like, if you just write SiO2, search, it should come on. Okay, SiO2. So okay, we should use this fused silica. The first one that pops up like Malitson, that's usually a good model. So if we double click on it, we added it, right? And now we check which domains are selected. And we remove with this minus the unit cell. So now we have only selected the cladding. Then we don't do the same, we just right click on material. We select blank material because we said that we were going to define gallium phosphide. So we do blank material, which we called gap in the label. We select the unit cell. And now you have down here these two things popping up, a refractive index, real part. I didn't do anything. I only clicked on the material. And here we are going to write N gap.
Which gallium phosphide are taking?
No, this is what we defined before with LAM and then gap. We should have done blank material. If you have done that N gap, but even if you haven't, like you can just put blank material and then write here 3.05 instead of N gap if you haven't done the definition. Then now let's move forward with the periodic boundaries and all of that. So
Then for me, to use silica is not there.
it's not there. But I mean, you know, pick one that has a range between 1.55 microns. But you looked for it as SiO2, right?
Yeah.
Okay.
You look for fused silica, you can find it. If you search for fused silica, then you can find it.
Okay. What is the? It's 3.05 if you just want one number. Are we all right? Okay. So now electromagnetic waves, we right click and so the perfect electric conductor is already there, right? They put it everywhere by default. So we right click on electromagnetic waves and we select perfect magnetic conductor because we need to put a symmetry plane at the bottom. Because we said we are only simulating 1/4 of this structure. So perfect magnetic conductor. Then what we need is these three faces at the bottom. You just drag it so that it flips a bit and you have access to them. And you select the bottom plane. Then, now,
What do we do with the bottom plane?
you select it. You just click on the faces. They should light up when you go on them. It's just these three domains. It's like 1, 2, 3. You just need to select the whole bottom plane. And then, so now the perfect electric conductor is going to be everywhere but down here. Okay, now it's not very visible, but the bottom one has been overridden. Now we have to put the two periodic boundaries, right, to make this infinite. So we go to periodic condition. You right click on electromagnetic waves and then you find periodic condition. Right? So we go, type of periodicity, we said it was a Floquet periodicity. And then now we have to add this kx that we defined before on the x direction. And what we select are exactly these two domains on one side and the two on the other side, such that it's going to be exactly periodic, you know, in that direction. Now, if we are here, we should go to the mesh. Now, the mesh, what we need is, one moment. Yeah, nothing. We have these boundary generators, right? If you right click on mesh, there is boundary generators. Oh my God. So find wherever there is free triangular.
Yeah, they changed the.
Ah, amazing. Okay. Free triangular. Well, free triangular, as you know, like for the waveguide, is just a 2D mesh. So we're going to select the first wall where we put the first periodic boundary condition, right? So we are doing a mesh of this side, because here the important thing is, we said that this thing has to be periodic, right? Which means that one face has to be exactly the same as the other one. So what we are going to do is we make a triangular mesh of this wall, this side, and then we copy that mesh exactly on the other side without leaving it to COMSOL that maybe it's going to make two different meshes. Because then if you put them, if you stick them next to each other, it might give you problems. So free triangular, we do size. And here what I had that it's supposed to be good, you say custom, and then you select the maximum element size to like 70 nanometers, and I have a maximum element growth rate at 1.2. We build it and it should look like this.
Yeah.
Now, we haven't finished clearly. What we need to do is we need to copy one face to the other side. So we right click there should be copy face somewhere in your version. Yeah, and then should be copy face.
Yes.
All right, great. So you click on that, and now it says, which one do you copy where? So the source boundaries are these two that we just made, and then we select destination boundaries, and we do the other two on the other side, like this. If we build it, then, you know, it's going to be the same.
Can you check the size?
The size is 70 for the maximum element, and the maximum element growth rate 1.2. The others, you don't select them. This is already enough to make sure that the pieces are not too big. Now we have our nice boundaries. We need to do the 3D. So we right click on mesh and we do a free tetrahedral. And again, we right click and we do size. We are going to do two sizes because the offside needs to be less precise, less fine than the unit cell. So you have two sizes. You don't do entire geometry, but you select some domains. So let's do the cladding. And this, what I decided to do is to put for the maximum element side, use this lambda 0 that we defined in the beginning, divided by 15. So that means that the biggest domain is going to be smaller than 1/15 of your wavelength. So that's already, you know, it's not going to be super fine, but this is just the cladding. And then the maximum element growth rate, I have 1.1. And the minimum, probably it's not important. I have something like 3, but you know, if you build it, it's just going to be the cladding. Now, if you go to 2, to the second size, we do domain again, and we select our unit cell. This one needs to be finer. So what we select is a maximum element size of 30 nanometers. So now if you build it, it looks much finer, right, at the unit cell. All right. Now we are basically done. We have to just look for eigenfrequencies. We can look for two of them, two modes. It's just going to find the dielectric and air mode, unit terahertz. What I would suggest, usually it works best, is to say that you're looking for this mode for around, and you say larger real part instead of close to absolute value. Because sometimes it can find a weird modes depending on where your band gap is. So like this, if you select like 100 terahertz, now what it finds is the first two modes that propagate above these 200 terahertz, and that's usually the dielectric and air mode.
We only have eigenfrequency search mode method around shift and rectangle. And there is no manual.
There must be a way.
I did yesterday already.
And so what do you do? Can I see?
Yes. Well,
Okay, but that's all right. It's 100, you know? It's the same. I think it means the same thing as the. No? Oh my God! Can you even see? But don't you worry. Like it's that's the same thing that I have, right? Okay, we actually from here. So I think it's like looking about that frequency around sheet. Are we here?
yes.
So I hope so. Now maybe it gives us an error. Maybe not, but it might, and there is a solution. So if you compute, no, maybe it works. Ah, no, okay, right, perfect. Do we all have this error?
Yes.
Great. So we go to eigenvalue solver 1. Are we there? Because otherwise it will never work.
Yeah.
Okay. There is this value of eigenvalue linearization point, right? So it's basically starting the simulation from 0 terahertz. We will have to force it to start around our frequency. That means we are going to write, I think F0 is what we defined in the beginning. Yes. So eigenvalue solver, here we put F0. Right?
Yeah.
Now, if we compute, hopefully, it doesn't give that error. I can't now, but did you run it once? And you have the error. You go to eigenvalue solver 1, this one here. And then there is something that it says 0 terahertz. Yeah. Something like linearization around. You put F0. Yeah, because now it's going to run like start from a frequency around your frequency. But someone else is simulating here with our server. Did the simulation run for anyone? Because it should take like less than 2 minutes. It ran, so it's fine.
I can't find. Oh, that's okay. I still have the
But it's not. No, you should do that thing about my mom.
Mine.
Okay, yeah, it's running. Okay, great.
Yeah. Are we all running? Whatever. Sorry, it's too long.
Whatever.
Just use FEM.
I'm sorry.
So what you should have is something that looks like this, if you manage to run it. So nice, but not too much. I would suggest you to go to this little triangle next to the electric field simulation, go to multi-slice, then you can change the Z planes, because right now this plane on the Z direction is just not giving you any information, right? So instead of number of planes, you select coordinates and you put 0. So it's going to put it at 0. You see, now it's on the floor. And if you look at it from the top, you can see now the electric mode of this structure, right?
Yes.
Good. If you go back to electric field, you can also see the two modes. Here I have eigenfrequencies, I have 2. you see that the band gap is 28 terahertz, which is very big. And if you plot the other mode, it's going to have the maximum in the air, like in the low dielectric region, low refractive index region, right?
Yeah.
So these are your two modes at the edge of the Brillouin zone. They are T modes because we forced it with those symmetry planes and nothing. So you see where this goes. Now there should be that exercise, but we won't manage now. So this took way longer than I thought. So what I would suggest you is to do it. And I'm just going to read it so that you know what you were supposed to do, and maybe also give some information about in which way to solve it. So what I wanted you to do was to find the optimal parameters for the key band gap of this unit cell. So, and also I would have liked the external granulation. For that, in that folder that was shared with you, you will find the COMSOL model with all the different geometries. So you'll find the hole that we just did. You will find the external granulation with a sinusoidal modulation, so it's not a rectangle. And you'll also find the pillar, just a rectangular pillar. So you should try to play with like how the geometry, how it changes, how it affects the band gap. So I think it's important that I say here now, like then you can do the exercise, but if you don't manage, whatever, what I tell you is that the pitch of the waveguide is what determines mainly where the band gap is in frequency. So now we saw that with a pitch of how much, 500, we used, I think 550 maybe, 500, okay. We saw that the band gap was between 150, 175, something like that. So it means that the center frequency is what, 163, something like that. So if you wanted to bring this band gap up to 193, it means that your pitch needs to be reduced. And that goes in the direction of those formulas that I showed you before about the lambda quarters. It means that the thicknesses that we picked were too large overall. So you'll have to reduce the pitch to bring the band gap up. Then, as we said, that the refractive index contrast is what is going to affect the most how big your band gap is. This means that the radius of the hole, like the bigger you make it, in theory, like the larger the band gap. You should see, if you simulate it by doing like a parametric sweep of the radius, you will see that if the radius gets too large, then basically this alternation of the layers is not good anymore. Now the low refractive index one is too large, and you will see that your band gap is getting smaller again. So there is a sweet spot, and I'll show you my color maps where it shows you how these things change. What I want to say as well, because it's important, is that if you simulate the external granulation, you will see that the band gap is smaller than for the holes. And why is that? In the external granulation, so let's say we have a small waveguide with, let me just put this slide here. Yeah, in this case, we have a small waveguide with this modulation of the sidewalls. So I'm telling you that the band gap is going to be smaller than in the case of the holes. Can you think about a reason why that would be? That it's small is true. I'm telling you. So we said that the band gap depends on the refractive index contrast, right? So what you see here is that here you have the perturbation of the material of the refractive index right in the middle of the waveguide, right? So that means that that's where the intensity maximum of your light field, the light propagating, is going to be, right? In the middle of the waveguide, not on the sides. If you have the fundamental mode, you know, beautiful. In this case, you're not perturbing the center where you have the maximum of the electric field, but you're perturbing the edges. So that means that your effective refractive index of this region, it should be larger than this part here where you have the hole in the middle. So your index contrast is not as large. And that's why you will have a bandgap that is smaller than the case of the holes. As a solution, if I want to close this chapter of the different solutions, you will see, and it would be nice if you did it, but what I wanted you to do mainly was to check where the maximum of the bandgap is for this structure. If you change the width of this portion here, you will see, of course, that the larger it gets, the smaller the refractive index contrast, so you're going in the wrong direction. The maximum of the bandgap for that structure is when it becomes this structure. Because like this, you are basically, you have, this is like from the textbook, you know, like the two layers are exactly those two layers. You can simulate them, like you track a waveguide with this width, how much it is, and it's just air, or a waveguide in silicon oxide, I don't know, something like that. So that's when the maximum happens. But of course, you will see in the session later for fabrication, something like this will have much higher losses than something like this, because the maximum of the electric field here is still propagated in the waveguide. It doesn't see any sidewalls in the middle. Here, you have an abrupt change that if the fabrication is not perfect of the sidewalls, every time you find an edge that has like some roughness and so. So in the end, what I'm going to show you now are my results for this structure. They have very large bandgap. The sidewalls are fine. And also the maximum of the electric field is in the middle of the holes. And on these two sides, above and below the holes, you don't see any roughness. You only see it here close to the holes. So I think it's a good trade-off. Of course, the holes are small. You need to be able to fabricate them. It's not easy. It's much easier to do the other two. All right. So, yeah. Yeah.
In terms of performance, it's better these holes or the
For me, yes.
Okay.
But if you have a good process in the clean room for your materials, then the holes are very good because they give you a nice bandgap. The question is, do you have a good quality factor? Like, are the losses low enough? And that depends on your process, your material. For silicon nitride, usually people use the external accumulation. It's easier to fabricate, but they have bandgaps that are much smaller.
You do these holes by these.
Yeah. Yeah, okay, that depends on the material. For gallium phosphide, the holes need to be very small. Like the radius is like 130 nanometers, something like that. Okay, so here I'm just showing you papers. So then if you want, you would look into them of like photonic crystal resonators that can be both Fabry-Perot, like the ones I'm going to show you later, where you have these two mirrors and the light bouncing back and forth. Or people have also like made photonic crystal ring resonators, basically with some roughness inside the ring, so that you know, you can have nice things like splitting of specific resonances. You can get an integrated dispersion that looks like this, oscillating. It stays closer to zero, and especially if it could cross the zero, you should know that every time you cross, you get a dispersive wave. So it's like your efficiency in the frequency conversion is good, better than if it just goes up and it's very misaligned with the cavity. Okay, you just do this. This in the middle is my work for gallium phosphide. As you see, I'm using these holes in the waveguide. In silicon nitride, people are using mainly this external modulation of the sidewalls. What I want you to focus on is that for the silicon nitride, they had intrinsic quality factors of about 4 million, but the mirror was non-chirped. That means that they just picked the dimensions and they repeated for 100 unit cells the exact same unit cell. So that gives you high reflectivity, but for a narrow frequency range. Here, what we did is to use like, okay, here is not very clear, but I can assure you that the pitch between the holes from this one until this one, it changes. And so we are targeting a much broader frequency range. With only 30 unit cells, we were able to get a polygon that was spanning like 25 terahertz instead of like less than 10. So also people nowadays are also trying this inverse design. It's like trying by FTTD to maximize the reflectivity by using this type of weird things. It's like, it's hard to fabricate because if you simulate something, it should be exactly like that. But with this method, often it can also be that you have very small holes to pattern. It's not very reliable, and also they didn't get very good quality factors. Sure, they used a few unit cells. Is it good? I mean, it's something, you know. Okay. My resonators, they look like this. You have simulated the directional cover apparently, so that's how we are covering the light in. The light bounces back and forth. And what I want to focus on is that the band gap along the mirror over here, it changes like this. And I'm going to show you in the next slide why. What I want to say is that basically what's very nice about these resonators, and this is mainly what you're interested in, is that while the dispersion of a ring resonator is linked to its cross section, and usually to have anomalous dispersion, you need a narrower ring, a narrower waveguide, which means higher losses from the scattering on the sidewalls. What you can do here is to pick a normal dispersion waveguide in the middle that is going to be larger to minimize the losses in the biggest part of the resonator. This is not up to scale, like these things are like 15 microns, and this is like 1 millimeter, you know, 500 microns. So you can reduce the losses in the waveguide by picking a wider waveguide, but then by designing the mirror such that they contribute to anomalous dispersion, you can still get anomalous dispersion overall. And now, how do we build an anomalous dispersion mirror? So you start from a waveguide, right? It's a small waveguide, like it's a waveguide without a band gap, clearly, otherwise it would be a photonic crystal. So you don't have a band gap. In order to transition from the waveguide to the mirror, you need this transition to be adiabatic. So you need a section of the mirror where the holes are small and the band gap is small, so that you can open up the band gap from 0 to large. So what we do, and here you see the first few holes are very small. What we are trying to do, these are two color maps. Here you see the center frequency, here you see the T band gap, how big it is. What you need to do is to start from a high frequency and bring down the band gap. Why is that the case? So the FSR of the resonator, we know for anomalous dispersion, the FSR should become larger, right, in frequency. If it gets smaller, it's normal. So in a ring resonator, you play with NG, that depends on the cross section. Here, what you do, you play with the length. So what you do? You make sure that higher frequencies are reflected first, so that the cavity length for this higher frequency is shorter. Like that, if the cavity is shorter, the FSR will be larger. The lower frequencies we propagate more inside these photonic crystals, so that the effective cavity length for this frequency will be longer. That means that the FSR is smaller. So like this is how you can get anomalous dispersion. So what you need to do is to bring down this band gap such that first you reflect higher frequencies, in the first part of the mirror, and then you reflect lower frequencies later on. So we start from a high frequency, very small band gap. We go a few unit cells. Here I have like 10 or 15. We go to a point where the band gap is very large. Now we are fine. We had our transition. It will not contribute many losses, you know. And now what we do is we scan across like the frequency range that we want to reflect. So we stay in a place where the band gap is large, but what we do is we move to lower center frequencies. And this is what happened basically in this plot here. So distance into mirror, you're coming inside with a frequency like 200. You get here the band gap, it goes back, right? But for 180, it will get all the way here. So the cavity is longer. So that's why we move the band gap downwards. And now to quickly go through it, I just want to give you like a methodology of how you would simulate the dispersion of a resonator. So you have your resonator, like your mirror, like we designed now, with these parameters varying like that. What you do, you can simulate that whole thing, like the mirror and hopefully even the taper, all this portion with numerical. You can just create a simulation box around this, right? You put a port here and you inject the light this way. Like this, what's important is basically the phase of the reflected light. So you want to reflect the light first of all, and then you know that the group delay of the PCR or the taper and the PCR is going to be given by the partial derivative of the phase of the S11 parameter, that is basically the reflected light with respect to frequency. So if you make this derivative, you can get the group delay of the PCR. From the group delay of the PCR, okay, if you want to do the whole cavity, then what you will do, you take your beautiful simulation of the waveguide in 2D from COMSOL. You can get beta 1, you know. You multiply by the length, so you know how long your waveguide is, and you get the overall group delay of the whole thing. When you do that, then what you have is the D1 parameter, like the FSR. D1 over 2 pi is going to be equal to 1 over tau dot, right? I don't know if you ever saw this formula, but it's the best that you can do to calculate all the higher order D parameters. If you solve this thing for D2, it will give you exactly the formula that you should know, like minus C over mg beta 2 times D1 squared. Yes. It will give you exactly that, but here you can calculate exactly all the other parameters. And all you need is just D1 as a function of frequency. You just can do the derivatives of D1, and then you multiply by D1 how many times depending on the order. So it will give you all the parameters. Honestly, this is a very important formula. You don't need to extrapolate any other formulas with beta 2, beta 3, all of that. So then you can also calculate the GBT. Just take the derivative of tau dot with respect to omega divided by 2L. Now the question is, what's the length of the resonator? Like we said, of course, the straight waveguide is very long, but depending on the frequency, the penetration depth changes, right? So you don't know exactly how much it penetrates inside this photonic crystal. So what you can do is just, for a short mirror, you can just approximate a constant average penetration depth. I would take it like in the middle of the mirror. It's already better than nothing, you know? If it's a short one, it doesn't matter too much. And so this is just to show you like some results from those FTTD simulations. Like I can't show code because of IBM, so I can only show you what comes out of it. This is the S11 parameter that you would get from the port that you put in your FTTD simulation. So the phase of this parameter is the green one. You can just take the real and imaginary part and get the phase out of this S11 parameter. It's very straightforward. I'm not showing it, but there is the model on the folder. I put like the FTTD model of this photonic crystal reflector. If you want to look at the model, how all the parameters are set, you can do it. But if you take the S11 that comes out of it, if you run it, then it will look like the green one. What you need to do is to unwrap it, because of course the phase is between pi and minus pi, right? So there are these discontinuities, but you can just unwrap it and this is your phase. That's all you need. If you do the partial derivative, like derivative with respect to the frequency, then you get the tau, you have everything. Yeah, okay, I took that the average penetration depth in my mirrors was about 10 microns. And this is just, again, if you do the FTTD, then now you don't just take the phase of the S11 parameter, but you take real and imaginary part and you calculate the magnitude, then you get the reflectivity. And so we see that the reflectivity of this mirror is very high, especially within 190 and like 205 terabits. We are like 99 point something, a lot. So it's quite good. And that's also why we managed to get solitons out of this, because we had very high quality factors, at least for gallium phosphide. And just to show you that if you use this method, your dispersion simulations and also measurements, like here the blue dots are just a fabricated device measured in the lab to get the positions of the resonances. Compared with the simulation, they match very well. So I gave you these formulas, but it's pretty straightforward. If you want to implement it in Python, it's just a couple derivatives, and you can get all your parameters from just this S11 parameter. So this is actually all. I hope you learned something. I hope you'll do some exercise, but at least I told you like how those configurations change and how, if you want to simulate the dispersion of this resonator, how you can do it. And I hope that you bring with you that ring resonators are not perfect, like they're very good, but if you want to, let's say, engineer the dispersion of a resonator like point by point, like frequency by frequency, here you can do it by engineering exactly where in your photonic crystal each frequency gets reflected. This is something that with ring resonators you can't control well. So either you get into these internal correlations to the rings, or some waveguide width variation along the ring, something like this. But this is actually a good solution if you have a high index material, like here we had gallium phosphide. Silicon nitride doesn't seem to be the best candidate for this because the refractive index is not high enough to be able to get a good reflectivity with few unit cells. So it gets a bit bulky. Still, they proved that with non-chirped mirrors, they can get results quite close to the ring resonators. So that's still good, but I would support more these applications for like 3-5 materials with high refractive index and something like that. This is it.
Any questions for Alberto? Welcome to you, ladies. Okay, good. Alberto, thank you very, very much for joining us here this morning. We have a break now. You guys were saying there's too much food, so the drinks are there. We do want to do some of the recordings here during the break that we talked about yesterday. So could we maybe we'll get like down 3 or 4. So for those who want to start now, we'll do with Gregory some of the recordings for the website. Yeah, so you can see it here in the front, and there is a break anyway for welcome space. Some light. Yay.
I really thought that 3D would take much shorter, but then to make sure that people were following, it's not easy. Yeah, and to be honest, I mean, those things that I talked about, it was also a lot of maybe also to wait for the simulation to run. So to be honest, in the end, I think it was that people learned to do without surprisingly. Like, how long was it? 1.5, I think, the questions. Yeah.
You know that like people say this first.
Yes. Thank you for
Yes.
Oh, he's awesome. But do you know why this option? It's called all the play.